Newton's first law says, a body remains in a state of rest or of uniform and linear motion, provided it is not forced to change its state by acting forces. In fact, we know that Newton's laws have a small flaw, because they are only valid for a linear movement, which in reality hardly exists. Instead of correcting this deficiency in order to improve and further develop Newton's laws, which should actually have been done, some claim that Newton's mechanics are already completely clarified, and that classical mechanics is outdated, inadequate, and uninteresting. The essence of Newton's laws, the real and the concrete, was deviated further and further. In reality, a body does not only remain in a state of rest or uniform and linear movement, not only when it is free from acting force, but in all of its states, and opposes all acting forces that force a change in its states. Now, with the new knowledge of inertia, we have explained how a body in curve motion, in all its states, remains in opposition to all the forces acting on it. With a natural force that a mass body naturally possesses, the inertial force. This can be described with a simple formula. When the radius of inertia is infinite, the curve motion, which is motion in general, is a straight line. Then the inertia of the body is zero. And the body with zero inertia remains in its state against the zero acting force, as Newton had described. Conversely, if we consider Newton's straight line as a curve with an infinite radius and Newton's rest as motion with zero velocity, Newton's first law is only a special case of inertia. Thereby Newton's first law is generalized. Hence, Newton's first law can generally be formulated something like this. A body remains with its inertia in all of its states, speed, distance, and position, counter to all external forces that from all spatial directions to force states of the body to change. And the inertial force with which the body remains in its states is proportional to its mass and the square of the speed, and inversely proportional to the radius. Newton's first law is also called the law of inertia. Well, it really deserves to be called this name. We see that the strength of the inertia of a body moving with v in general depends on the radius. This indicates that the physical effect created by the momentum can be different with the same velocity v and a different radius r. So speed is not always the same as speed. This means that the previous momentum is only a special case. That's Newtonian. Thus, the law of conservation of momentum is generally called into question. One likes to prove the conservation of momentum with this Newton pendulum. But we can also use a similar device in which the balls hang on threads of different lengths. It could look something like this. This proves exactly the opposite, that in this case the momentum is not conserved. So the law of conservation of momentum is generally incorrect. Newton's second law says, a body acted upon by a force moves in such a manner that the time rate of change of momentum equals the force. Because inertial resistance always compensates for part of the force acting if the body does not move in a straight line. So Newton's second law is also only valid for linear motion. Therefore the familiar differential formula for acceleration, a equals dv/dt, does not generally apply. In general only. And the speed accelerated by at its maximum can be calculated using the following equation. This means that the maximum speed of a body accelerated by acceleration is limited to. Also, the previous speed formula for an accelerated body v equals at is only conditionally valid. This law, Newton's second law, will only be complete when the persistence property of the mass body is integrated into it. So we add the inertial acceleration to this theorem, stating that a mass moving at speed generally has a drag acceleration that is proportional to the square of the speed and inversely proportional to the radius. Then Newton's second theorem can be supplemented as follows: a body acted upon by a force moves in such a manner that the time rate of change of momentum equals the force minus the inertia of the body. When the radius is infinite, the body moves in a straight line and inertia is zero. Then Newton's second law is available again in its original form. Newton's third law says, forces always appear in pairs. If a body A exerts a force on another body B, an equal but opposite force from body B acts on body A. In our opinion, this law is actually only valid in the area of statics. Therefore, it should be supplemented by inertia, especially for dynamics and kinematics. The moving body always opposes the external force with an equally force. However, this is at most as follows. In short, if the inertial force is integrated into Newton's laws, which actually only describe snapshots and special cases of motion, Newton's laws are completed and generalized with regard to the motion processes. Thank you very much for your attention. See you next time.